Started then. I'm from my position, I can't exactly see the presentation, so I'm just going to kind of run through the concepts and go through it with you. One comment I would like to say, I was really fascinated by Dr. Barrera's connections with the harmonics and with the quarks and those types of things. I was actually running some numbers while he did that, and it really does look like he's onto something where there's some underlying symmetries that he could latch onto. So that was very, very interesting. How I did that was by applying this equation that I had to it, which gives me a little different insights, and I'll explain that. So I want to obviously thank you for inviting me here again. This is going to be my fourth presentation. So the first presentation to the Global Scientific Guild at a webinar for applied science and technology was the seventh. And at that presentation, the MEQ, or what I'm calling the McGinty equation, was very fledgling, very new, and it was still very much in the stages of needing other experts to verify and validate it. Since that time, there's been 7 papers published in double-blind peer reviews in the International Journal of Theoretical and Computational Physics, which has satisfied that requirement. So I've been moving on full steam ahead, and in this particular presentation, I'm going to talk a little bit about what has happened with the research that Skywise AI has been doing, which is my AI stack and a team of experts that I have. And since the time of the 7th conference, when we first presented this, was just maybe about a year ago to now. So we'll kind of get started with explaining what it is. So not everybody here may know what that was or was here at the 7th, so I'll start kind of from the beginning. The MEQ, or the McGinty equation, as I'm calling it, is called that really as a utilitarian function. I needed to call it something when I first invented it because its actual name would be the unified equation of quantum field theory, fractal geometry, and gravity, which is kind of a mouthful to say and a lot to run through. So AI had agreed with me that that would be a good way to kind of call it that, rather than having to type out this formula every time. The formula here is broken down to show you exactly how we got to this. This is a very simplified formula, and we can do many different things with this in terms of modifications, and which I'll get into in a little bit. But this portion right here, this is the solution of the free quantum field theory. This is the Schrodinger equation, which is basically the foundation of quantum mechanics. This is the wave function of a particle. So that's where we're going to start, because we know that has been empirically proven, and that's what all quantum mechanics is based on. This, again, is the solution of the free quantum field theory. Here, this is where the kind of the magic happens. We put this fractal correction term in. And what this does is this takes in some different parameters of, this, of course, the space and time, and then the dimension, the mass, scale, charge, and the scale. The scaling factor is huge, because what I can do with this is you can scale infinitely down and infinitely up in fractal patterns, which becomes very, very useful. Then this last portion here is gravity, and what this does is this brings in general relativity, which has been tried and true and proven, in many, many cases. So that's kind of what we've done, is we combine this all together. We've taken quantum world, general relativity, and then blended it with quantum field theory and fractal geometry potential. So what we're trying, the original purpose of this was to kind of find a fundamental, theory of everything per se, but really just like a unified equation of fractal not even fractal geometry, of quantum field theory and general relativity. That's been a problem, right? So I first kind of set out by saying, well, let's use some of Mandelbrot's and Dirac's ideas and see if we can get a really, really advanced AI to do the math that humans really can't. And so that ended up happening. And that's kind of the origin story of how this thing came about. And I was just, I guess, aware enough. I wouldn't say I was smart enough because I didn't understand it when I first started diving into it. But I was aware enough to know what it could do and what was possible. And so that's really been the driving for, let's say, the last year and a half. Why this is important is it does create a unifying framework that unifies quantum mechanics and gravity quite well across all fractal scales. By including that fractal potential term, what we're doing is we're creating a method of finding self-similar structures across many scales, from the galactic to say, the Planck scale. And it also, interestingly feeds into harmonics, string theory, many other theories. This pieces together quite well, and the math works very well, which I'll show as well too. So we bridge the gap. We're looking for many different applications of this. This is not an algorithm for quantum computing. That's one thing it can be used for. It's actually quite a bit more than that. I think when the science world and people kind of start catching up to what's going on in the entrepreneurial world and in the business world, this is a fundamental equation that is new and is very, very useful. And I would my big goal is to spread the knowledge and transfer the knowledge to people who can use it, like those that watch these webinars. The goal, again, scientific exploration. We follow strict scientific guidelines. We use AI models that are highly, highly academically trained. We want to, continue to validate and refine these models that are going into, and we're leveraging the equation for new technologies. And we're having AI do the math and tell us how, and validate it and do some really amazing things. So this is kind of what we're currently working at. There's certain groups of things that we're kind of focusing on at this point in time. So the scientific modeling and simulation, we've gotten very good at that. We can do that almost as like a science as a service type of a thing, where we can apply that to specific use cases, or we can apply it to entire fields of study. We're looking at new medical diagnostics treatments plans. We've developed new proteins that have much greater efficacy, fewer side effects. All of these things are coming out in very, very precise simulations. That includes cancer and some other major diseases that we didn't have this AI technology prior to even look at it. Renewable energy sustainability, that's huge. That's kind of where I focused initially, because that's the low-hanging fruit per se. Hydrogen splitting semiconductors, hydrogen splitting spark plugs, these are designed, these are prototyped. All they're waiting for right now is to get put into scale and into production. 0-point energy harvesting production, the math and the theory is done. It's been validated multiple times. It's been validated by experts. Cold fusion, people may laugh. See, what I've found is people ignore, then they laugh, then they fight. And that's what Gandhi kind of found as well too. But that's what's kind of been happening is, so when I say cold fusion, people go, ha, 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 ha. But no, really, we've got amazing results with helium isotopes and the production of it, plus schematics for it. So there's some really amazing things that are coming. Part of this is this impact on artificial intelligence and machine learning. That's what we're doing. We're enhancing the capabilities of AI with these machine learning algorithms, and it's already starting to have a good effect. So quantum field theory, if people don't really quite understand this. This is kind of a strange thing. This kind of posits that the universe, or all things, all existence, is contained within one, call it a plenum of energy, that all things are in one thing, and there really is no true separation. And we can measure this through the quantum field. And it's very powerful, and it gives us a way to find very exact and precise positions of orbitals and of these places by measuring the perturbative effects of gravity on the quantum field, on the gravitational field. What that does is that gives us a precise location, meaning we don't have the probability anymore. We're not looking for where the orbital is. We're measuring where the perturbation in the gravitational field is, which is very precise. And so what we're doing is we're actually using that fractal perturbation to find those things. And in doing that, that also allows us an ability to regulate the Heisenberg uncertainty principle, because that's something that's where 50% of the time there's nothing exists, 50% of the time it does. However, when you can measure a thing, I've found that you can regulate a thing, not control it, but regulate it. And that's all we need to do for some very, very amazing applications. Fractal geometry, touch on this a little bit more. This is, many of us have seen fractals. If you're not familiar with Dirac, Mandelbrot, I mean, geniuses way ahead of their time. We're using fractal geometry to deal with some fractal dimensions that solve some problems that string theory had brought up nicely, works some of those higher dimensional ideas in, and it also gives us some scaling laws, so we can work from a micro to macro and have feedback between the two. So it's a constant feedback loop, like reality, where the quantum communicates with the cosmic and the cosmic communicates quantum. This whole framework is built with that same idea in mind. The fractal correction term, the dimension is the dimension of what that you're going to be in. You have to pick a fractal dimension, which adds to complexity. The charge is, of course, the electric charge. That's important. Thermodynamics comes into play with this too. The mass is important, and then the scale at which you want to see it. So you can find and do some observations at the quantum scale, and you can scale these out to our scale, the event horizon scale, or to cosmic scales as well. This perturbation, again, I explained a little bit of this earlier, but this is where we're incorporating gravity into quantum fields, effectively creating a way to measure quantum gravity. And that's what we needed in order to make some of the further breakthroughs down the road. This comes into play with quantized inertia, which is from Mike McCulloch. He's in Oxford. That's a correction to Newtonian inertia, Newtonian gravity, a slight correction, which makes a big difference. It eliminates dark energy and dark matter. We don't need those anymore because it helps to explain the rotations of the galaxies without all those things. So that's been incorporated into this as well. These are some of the things that we look at when we're looking at the perturbation effect. The biggest thing that we need to find, or where we're seeing the biggest results, is the propagation velocity. But there's many other areas, again, the coupling strength and the normalization factor, some of these other ones where we can find these great measurements with the MEQ framework. So what's all this mean? So what, I guess? Okay, great, it's math. So what are you going to do with it? First part we're going to have to do with this is to apply it to quantum computing. Many of these applications require powerful quantum computers that are error-free. And luckily, there's a scientific paper that's been reviewed. It's already published on how to do that. So once we get the right team of people put together, we will be able to do the error-free quantum computing that's necessary. But for quantum communication, this opens up some really amazing ways for us to use entanglement and even quantum teleportation in ways to transfer data that's highly secure. And due to the nature of the quantum world, if you look at it, it changes. So it's immediate. There's no eavesdropping, no hacking, nothing, because if there's any observation outside of the private keys, it's immediately detected through quantum mechanics. So it makes it very viable for protection of data. We use quantum key distribution and entanglement-based communication. So this is where there's two different ways of doing it, but the QKD is an important factor in this because quantum security, many people don't realize this, but future quantum computers will be able to come back and decrypt any data that exists today that is not quantum secure per se, or that isn't resistant to that. And so there's a push for, especially for diplomatic types of things, for people who want to have the secure quantum proof encryption. And really there's something called Kyber, which is a language. It's a lattice-based encryption, and Kyber keys. We've been using our equation to develop some using that method, which is completely quantum proof, to help develop some of those things for some clients and people that are looking for that. So with this quantum communication, we're going to be using the fractal geometry comes into a play with it for the different patterns. Really fascinating stuff coming out on 6G antennas, and we're not stopping. I mean, we're working on the 6G stuff I shouldn't say is done, but a lot of the design is done. But we've already moved on. You can jump. You don't need 7, 8, 9. You can go terahertz and just design straight there with AI. You don't have to. So we're going to see major jumps. We don't have to go 3G, 4G, 5G, 6G. We can go from 5G to 6G and then go to terahertz. We don't have it's a new era in science and with AI. The quantum internet, that's with these QKDs and keys and instantaneous communication protocols, will completely revolutionize our internet and our connectivity and the security of it. So that's in development as well. This is kind of how we build that. There are some quantum nodes that come for kind of the first part of this. These are basically the architecture, the structure of the network. We have quantum channels that go into the nodes that use different quantum states and entangled protons. We have repeaters that will then go into here, which creates the network, right? And then we can integrate with the classical network structure. And then we have a control network that can monitor over the entire quantum network as well, and make sure that the resource and allocation. So it's again, that's a big project, but that's how it's going to be done. The quantum cryptography, I spoke about this a little bit more. We are also implementing some other methods, such as the MEQ fractals, where we can implement a fractal pattern in addition to the hard AES, and which is advanced encryption standard. That's what most banks use right now for financial things. It's very effective, but it's not quantum proof. And RSA, that's another one that's used quite right now. Again, these are ones where it's encryption that's based on a hard problem. So it's a very big computational problem, which is incalculable for most computers. So but not for quantum computers. So that's why we need these quantum-based algorithms, like the lattice-based Kyber. We have a fractal-based algorithm that we've put together using the MEQ that has infinite scaling. So that's, again, quantum proof. And then we're also using another one, we're using fuzzy logic. So the fractal patterns and the fuzzy logic are not what you call hard problems. They can't be solved by computing math. There's other factors that go into it. But the RFU, which is the neuro RNA Fisher unity, it takes the Fisher information and creates, you have to know the number of pathways and also the Fisher information that goes along with it. So it really creates a major problem for hackers or bad actors out there that have been causing havoc for a long time. Artificial intelligence can be quantum enhanced. There's the parallelization of AI tasks. And then once you start putting these in with GPUs that NVIDIA makes that are dual processing, it's speeds way up. So there's some really cool things that are coming out of NVIDIA right now too to keep an eye on, like photonic quantum computing. That's another one too, where we can start using light. We can, thermodynamic computing is another method that we're starting to look at much more closely, because really what this equation is it's a new lens, is all it is. It's a tool. It's not anything magical. It's just really, it's like a lens to be able to see the very fine, minute things that we weren't capturing before, because we didn't have a tool to deal with probability and deal with the uncertainty principle in that. But this is what this does. So in energy and environment, we've got a lot going on there. I touched on a few different things. For example, the hydrogen splitting spark plugs, cold fusion. There's major advancements that we can make just to solar panels and solar cells enough in order to have them capture more energy. There's advanced materials, very high density type materials that we can create. And it even goes as far out as, we have the math and we have the simulations, to actually generate and create micro black holes and contain them and then extract energy from them. And it goes even further from there. But the amazing thing to me is that AI and the AI assisted math and technology has come so far already, so far. Yet most of the academic and science worlds are still trying to figure out how to use ChatGPT to write. I think we're going to see some really amazing changes once some of these technologies get to the manufacturers like Intel and IBM that will make the changes. And because there's profit in it for them, that's why they're going to do it. Let's not kid ourselves. But it will help everyone and help the world. So that's kind of what the goal is. And we want to do, the efficient hydrogen production, clean energy, and with the semiconductors, these are more for solar energy. This is going to take straight sunlight and turn it into storable hydrogen energy. Hydrogen splitting spark plugs are a little bit different. Those would be spark plugs that are prototyped that would fit in a car with there'd be a kit that you could go into and you could switch over cars from gasoline to hydrogen. And it really comes down, fascinatingly, to getting the molecules to vibrate at just the right frequency. But we weren't able to figure that out without this tool. The same thing with zero-point energy harvesting. That's another one that's going to be, it's on the horizon. Again, a lot of these, this is theoretical physics, but it's, I'm not making any of this stuff up. It's highly vetted by advanced AIs. And as the experts look at it, one after the next, it hasn't been wrong yet. So these are some of the things that are on the frontiers that I welcome anyone to scientifically scrutinize and go for it, and move forward with some of these. Cold fusion, this is something that will revolutionize energy as we know it. There's a lot more to this. There's a lot of information available online, those types of things on our video, but that's something to kind of keep an eye on. Quantum-based renewable energy systems. So this is where we're going to be actually integrating the renewable energy systems to use the renewable energy to power the renewable energy systems. And then those systems can then store hydrogen and store energy in a way that we can then manage the ebbs and flows in the power grid so that we have stable power grids and stable power. And also we'll be able to produce hydrogen energy in remote locations with just generators that are remote that can do that. Again, there are a lot of these things are prototype. They just need people with a lot of money that want to build them, and we'll build them for you. Environmental sensing is big. This is going to really help with our control of the climate, or not control of the climate, but understanding the changes in our climate and understanding if what we're doing is having an effect and making a good effect, and then making changes based on real environmental data, real time around the world. We also have, this is basically, again, talking about how we're going to look at using energy, limitless energy harvesting, um, solar cells, batteries and energy, smart grids. This is the key here, though. This is, or one of the keys, is the sustainable materials. With the ability, as I talked about, to really hit to find the perturbations in the gravitational field, and with the precision that it has at finding these different electrical properties and thermal properties within the atoms, we can change some of the properties of them to make them have different properties than they have by changing the magnetic properties just slightly. So that's what's going to end up creating, materials that are as light as air and as hard as steel. There'll be materials that the superconductors that we've never couldn't have dreamed of that can now be created by using this tool with other tools, in order to reach new levels to create these battery storage and create these networks now. So it all kind of goes together. Healthcare has been very exciting. Protein design. A lot of AIs won't do it. We use a very, very highly academically trained one that has been producing phenomenal results. These proteins are, the protein folding is engineered with some of the quantum insights, and we're able to create proteins that are in simulations, have not gone through clinical testing yet, but have a much higher efficacy. They work better, and they bind better. There's many different types of things. So we're actually using the fractal qualities of the molecules themselves and of within our body to bind and to use even the targeting. So there's nanocarriers and then fractal ligands that would go into the design of these proteins. And then there's a fractal drug delivery system as well that goes with it as well too. So again, all of these are areas that I'd love to explore more, but I'm just trying to kind of run through the many things that have happened in the 1 year since we first presented this to the guild here. These are some the sensing, quantum imaging versus classical imaging. The resolution's much higher, sensitivity is very high. We're not with the speed. The speed is still about the same. That'll change, I think, as quantum computing has come up. But we're able to see things and visualize things in a new way, not like an electron microscope. It's much more of a AI simulated, based on very, very exact and precise measurements. Again, we reduce the noise, we extract the features, and we get the diagnosis. And AI is involved in all of that process. Some of the challenges we have now, again, there's limited resolution, low sensitivity, and it does take a while to get the 3D images with, for doctors. So this is going to be much quicker because it's kind of built into the math. There's many different things we can use sensors for besides math, national security, all kinds of monitoring types of things. People will find all kinds of new ways to use the quantum sensor information as it starts to become developed. These are some things that we've already mapped out, plans we've already put together for early tumor detection, radiation planning. We can do a lot of personalized treatment options using genomics, and again, applying the MEQ framework with advanced AI. This is a schematic that we have already of a cold fusion reactor. But so these are some of the other things that we're doing with the manufacturing. You can apply these quantum principles. Again, because it's an equation and the math works across all scales, and it has been proven and applied to so many different things, you can take this framework of equivalence, of Schrodinger, with the free quantum field theory, with fractal geometry, with that blend of everything that makes this beautiful equation. You can apply that to just about anything. You could apply that to psychology. You can apply, it's just a matter of understanding the variables and what variables you want to use and playing with the variables. And AI is really helpful with that. Yet another good use case for it. But we're optimizing processes, we're improving qualities, reducing costs. There's a lot of different ways in this method where you're looking, where the micro informs the macro and the macro informs the micro. You can you have a lot of interesting perspectives to take a look at any type of complex system. It could be finance, it could be healthcare, it can be any of those, but really any complex system, this tool will work well with. Supply chain optimization. I talked about financial systems. We can do, anomaly detection, financial optimization. That's something that people, once they figure out how we're doing that, they're going to be all over it. But it's just a matter of, again, finding the right resources, the right people, and teaching and educating people honestly about what this is and how to use it. This is, again, part of the first prototype for the cold fusion reactor. I wasn't kidding when I said we have detailed schematics for all of these things. This is an area where we're going to see much more improvement too. We can apply this framework to these quantum computing algorithms. So we can do some measurements. It gives us a way to, even to measure things down to the Planck scale. There's a number of different ways to do it, but this one seems to work for what we're doing right now. We can find ways. We need this quantum supremacy in order to do things like create real-time stabilized and contained micro black holes that can power stable wormholes. These are all vetted out theories and mathematics, but in real-time application, we're going to need the quantum supremacy and the parallelism and the error correction. So these things are all things we're working on, and trying to find a quantum computing company that is interested in doing those things. So they all kind of have their own plans. Quantum neural networks, that's another thing. We're familiar with neural networks. We now can apply the quantum algorithms and principles to these neural networks, which makes improved efficiency, enhanced learning, that as well. Quantum materials, I talked about this a little bit, designing materials that have different thermal properties, electrical properties, mechanical properties. All of those things can be done with this tool. Quantum controlled nanorobots, that's another thing where we're getting into that. This is part of the drug delivery system, but this is coming. It's already in labs around the world. But we can apply these concepts to that. Autonomous vehicles, again, it's another way of the micro informing the macro, that feedback loop. You get improved sensor data, improved algorithms, better safety. So that will eventually be worked into most of the programming. This is a picture of Sycamore, which is Google's it's probably the most powerful quantum computer in the world right now. But the quantum innovations are really the driving force, are going to be the key to actually realizing these things, because much of this is not computable by a classical computer. I would say NVIDIA's processors make that closer to being more possible, but the quantum technology is really where it needs to be. And this is kind of what I'm talking about, how on a quantum computer, we're looking at the speed in millions of operations per second versus an NVIDIA, platform here, and this is, IBM down here. So we're talking about a major boost in what we can do mathematically. These are the types of things we'll work on with the quantum computing. And so the key takeaways from this presentation is I wanted to make sure people understood how we're putting this together. This unified equation combines quantum field theory, fractal geometry, and gravity. So that's how we're merging general relativity and quantum mechanics. it can be applied in particle physics, quantum computing, which I've explained, material sciences, and any types of, we're looking at some really very fascinating advanced propulsion things. Again, pay attention to quantized inertia from Mike McCulloch. That's recently was published in the Royal Astronomical Journal or something like that. But that is a correction that needs to happen to Newtonian physics. And when it does, it opens up a lot of interesting things. And again, it answers the question by eliminating the need for dark matter, dark energy kind of immediately, which is kind of a hint that they're onto something. The market that we're looking at for MEQ type solutions, just in general, the quantum computing market, there's a big opportunity there in error correction. That's paramount. We have to fix that immediately. Energy harvesting, I talked several methods, everything from hydrogen to 0-point energy to cold fusion to eventually contain micro black holes. All of these things are in the works. Healthcare is a big thing, the proteins, advanced materials, transportation. So there's many different types of things for us to chew on and to get moving forward. The key right now is really academic acceptance, understanding the math behind it, trusting AI, understanding what AI is telling us, and then putting that into actionable, real world, tangible results. So really kind of the success or the future prospects of this is not, to be completely honest, it's not going to be if MIT or Oxford or Harvard decides, oh yeah, this is new, we're going to use this. That's not going to make it happen. The real test is going to be tangible impact and market adoption. Those things will cause these developments to happen, relying entirely on the establishment to recognize the things that are going on isn't happening as fast as I would like. Let's put it that way. It's not that it isn't happening. It just isn't as fast as I would like. So we are going outside of some of the academic partners and focusing much more on business and government type applications. Again, because people buy what works, and so we can prove that to corporate America much quicker than we can to the academic powers that be. So that's kind of what we're looking at moving forward. And that's a lot, but that's all I had for today. And I'm happy to answer any questions I can.